All right, so today we're going to start with chapter 2, lesson 1. We're going to be talking about relations and functions. So we're going to learn about how to analyze and graph relations, find functional values. We have a long list of vocabulary words here. So ordered pair, Cartesian coordinate plane, quadrant, relation, domain, range, function, mapping, one-to-one function, vertical line test, dependent variable, and independent variable. So these are all things that we're going to kind of go through and cover throughout our lesson today. So how do relations and functions apply in biology? It's an interesting question. So here, the table shows the average life and maximum life for some animals. The data can also be represented as ordered pairs. The ordered pairs for the data are 12:8, 15:30, 8:20, 12:20, and 20:50. The first number in each ordered pair is the average lifetime, and the second number is the maximum lifetime. So again, here's our data. Here are ordered pairs. Again, we're pairing a average lifetime with a maximum lifetime for each animal, and these are the ordered pairs here. So an ordered pair, right, is a pair of numbers that shows the average lifetime and the maximum lifetime. So now we're going to talk about graphing relations. So you can graph ordered pairs by creating a coordinate system with two axes. So you probably have some previous experience with this, but essentially each point represents one of the ordered pairs from above. So from the previous problem. So I took the ordered pairs and I graphed them on here. So again, here is the average lifetime and here is the maximum lifetime. So each ordered pair represents each point here on the graph. The vertical axis is the maximum lifetime and the horizontal axis is the average lifetime. So the graph of the animal lifetime data lies in only one part of the Cartesian coordinate. So a lot of times you see things going on vertically up and down, right? The y-axis and then horizontally with the x-axis, right? And the origin is usually in the middle. So this one here is 0, 0. Here is the vertical y-axis, here is the horizontal x-axis. So we are only seeing one quadrant. And if you know, right, you have the x-axis and the y-axis, it creates 4 different quadrants, right? So this is just really just showing one because it's the only one that's relevant in this problem. If there ever is a point that falls on one of the axes, it technically isn't part of any of the 4 quadrants, right? So it wouldn't be considered part of any one of the quadrants. It has to be actually out here. So if you ever have a y value of 0 or an x value of 0 or x coordinate or y coordinate, it will fall on one of the axes and it will not be considered part of any of the quadrants. So in general, any ordered pair in the coordinate plane can be written in the form of x, y, right? Our x coordinate and our y coordinate. So here's an example of a Cartesian coordinate, right? Here's the y-axis, here's the x-axis, the origin being in the middle. Here's a coordinate 3, 2, right? The ordered pair, the x coordinate, the y coordinate. So it would be 3 units to the right. It's 2 units up on the y-axis. And again, here's quadrant 1. Here's quadrant 2, quadrant 3, quadrant 4. And assume that each square in a graph typically represents 1 unit unless it's otherwise noted. That can get you into trouble sometimes, so please pay attention if there's any labels on the axis as to a different unit, make sure you pay attention to those. So a relation is a set of ordered pairs, just like the one we looked at with the longevity of animals. The domain of a relation is all the x coordinates, and then the range is a set of all the y coordinates. So the domain tells us the x coordinates, how far left and right something goes, right? And the range will tell us the y coordinates, right, how far up and down it goes. The graph of a relation is the set of ordered pairs on the coordinate grid. So what is a function? So a function is a special type of relation in which each element of the domain is paired with exactly one element of the range. So a mapping shows us how each member of the domain is paired with each member of the range. So here's an example of a domain and range. And here's the relation. And the mapping is this part right here, right? The domain is listed here, right? Here is the range listed here. And the mapping is we connect each one of the x values to the y values, right? Each one of the x coordinates to the y coordinates. So this relation here shows that we are mapping -3 to 1, right? 0 to 2, and 2 to 4, right? And this is an example of a one-to-one function because each one of the elements in the domain matches with exactly one element in the range. So here's a summary of this concept here. So here's an example of a relation, right? It's got 3 ordered pairs. This is the relation. So the domain, right? So the domain are all the x values, -3, 0, 2. And then we're going to go ahead and map it with the range. So range, again, lists all the y values, 1, 2, 4. And then we're going to go ahead and we're going to map it, right? Draw by connecting the x coordinate to the y coordinate, okay? And again, this is an example of a one-to-one function. One element of the domain connects with exactly one element of the range. Let's look at this relation now. Again, 3 ordered pairs in this relation. And I'm going to go ahead and put the domain in, right? Here's the domain, -1, 1, 4. And then I'm going to go ahead and list the range, 5, 3, 5. But if you notice, the range is listed only the element 5 once, because you don't actually duplicate stuff when you're writing out the range or the domain. So if you have the element come up twice, you only actually write it once. Okay, so here we're going to go ahead and map it out. So -1 to 5, 1 gets mapped to 3, 4 gets mapped to 5, and then this is where we see that -1 and 4 both get mapped to the y coordinate 5, because you can see here that's what the ordered pair says. So this is still a function, but it's not a one-to-one function, right? So each one of the members of the elements of the domain gets mapped to only one element of the range, but it is not one-to-one because there are 2 different x values that get mapped to the same y value, right? Very different than here. This is one-to-one because it's only a one-to-one match. These you have a duplicated y coordinates. Let's look at this one. So this relation has 4 ordered pairs. So again, I'm going to list the domain, right? Here I have -3, 1, 5. And again, notice that -3 comes up twice, but I only write it once. And then the range, I have 6, 0, 1, 6. Again, 6 does not get listed twice. It only gets listed once. And so, and you're noticing too that they're listed in numerical order, right? From least to greatest. And then I'm going to go ahead and map it out, right? -3 gets mapped to 0, 5 to 6, 1 to 1, -3 to 6. And again, you notice that -3 actually gets mapped to 2 different y values. So in this instance, this would not be considered a function because I don't have each one of the domain elements of the domain getting mapped to only one member of the range. This element in the domain gets mapped to 2 different y values or 2 different y coordinates. So this is an example of something that would not be a function. So going with an example here, trying to discuss domain and range. So it says state the domain and range of the relation. Oops, let me turn off my video. Shown in the graph is a relation, a function, right? So this is where we have to ask ourselves. Here's the relation, right? I'm going to take all the ordered pairs and write them out. Here's my relation, okay? So I have all the ordered pairs, right? Listed by x and y coordinate, surrounded by parentheses. And then I have braces on outside showing that is my whole relation. And then I have to ask myself, well, the domain, remember, is all the x values, all the x coordinates. So I list out all my x coordinates, again, going from least to greatest, right? -4, -1, 0, 2, 3. I don't have any ones that repeat. And then the range, now I list all the y values. So I have 3, -2, -4, 3, -3. Again, listed them in order from least to greatest. And then that would be my domain and my range. So again, this is my relation written out as a set of ordered pairs. This is the domain of that relation, all the x coordinates, and then this is the range, all the y coordinates. So each member of the domain is paired with exactly one member of the range, so this relation is a function, okay? This would be an example of a one-to-one function. So when we are trying to identify, you might ask yourself, like, how do I really know if something's a function? Well, one of the easiest ways to test if something's a function is by using the vertical line test. The vertical line test is a really easy way, especially if you have a graph available to you. So if the vertical line test states that if no vertical line intersects a graph in more than one point, then the graph represents a function. So here's an example of what that looks like. So here's my graph in blue here on my coordinate plane. Here's a vertical line. If I were to take this vertical line, right, this up and down line, and move it from left to right, at no point would that vertical line ever touch the graph more than once. It would only ever touch it in it would only touch it in one spot, right? It would never touch it more than once. So that would be different than and that would mean it passes the vertical line test. If it failed the vertical line test, that means that a vertical line intersects a graph in two or more points, right? Then that graph would not represent a function. So here's an example of that. So again, here's my graph in blue. Again, if I were to take a vertical line, and if at any point like this one, it touches it two or more times, then it's not a function, all right? Because that would show that your x value has maps to two different y coordinates, right? If any x coordinate maps to two different y coordinates, it's no longer going to be a function. But visually, this will make sense because look, here is where it would fail the vertical line test. It would touch at this x coordinate, it would have two different y values. So in example one, so this is going back to example one, there would be no vertical line that contains more than one of the points. So if I take a vertical line and move it across, it would never touch any one of those points at more than two, or it would never touch two or more points at the same time. So again, if I move it across, it only ever hits a point at any single time and never hits two of the points at the same time. Okay. So a little bit of a study tip. So I have this, red line that I get to move across my screen, but while you guys are working, a vertical line test could easily be done with a pencil or a pen, right? You just move it across your graph from left to right, and that would help you do a vertical line test on your own. So let's try one. So here's example number 2. And the table shows the population of the state of Indiana over the last several decades. Graph this information and determine whether it represents a function. So here's my x coordinate. Here's my y coordinate, right? These can be written out as ordered pairs. Here's a graph of what it would look like, right? Here's my x-axis, my y-axis. So these points represent this data right here. And so here's my vertical line. I'm going to do my vertical line test. So there you go, moves across. It only ever hits one point at any given time. It never hits two or more points at the same time. So this would pass the vertical line test, right? So again, you could use a pencil or a pen, run it across your screen there to see if it passes the vertical line test. And again, you will also notice that this would be a form of a one-to-one function because there's only one x value that ever pairs with one y value. Equations and functions. So equations of functions and relations can also be represented by equations, right? So the solutions of an equation are the x and y, the ordered pairs that make the equation true. So if you consider the equation y equals 2x minus 6, since x can be any number, the domain, right, would be the x values, and the y would be the range, right, the y coordinates, the y values. So to determine if this equation represents a function, it's often the simplest just to look at the graph, right? So let's go ahead and graph this. So here's the relation y equals 2x plus 1. Kind of the easiest way is to make a set of ordered pairs. So I can take these x values and substitute them into my equation to find my y values, right? So I put -1 in, right? 2 times -1 is -2. -2 plus 1 is -1. So again, I could do this for all these values, right? Put them into the equation, get my y values. right? So I've made my table, and then I'm going to go ahead and make my graph. So here, my graph, I can see that it is a line, right? And hopefully you remember that this is your slope and your y-intercept, slope y-intercept. That would be another method of doing it. And again, if I were to want to find the domain and range of this, right? The domain is, again, all your x coordinates, right? So this would have x coordinates ranging all the way down from negative infinity all the way to positive infinity. So my domain would be all real numbers. And my y coordinates, same, they would go down to negative infinity and go all the way up to positive infinity, which would be all real numbers as well. So my domain and my range are all real numbers, right? So I'm not going to list them out because there's an infinite number, right? And then the next part is, can we determine if this relation is a function? Well, we can easily do the vertical line test because that is, I have a graph in front of me. So again, you could take your pencil or your pen and just run it across your graph. You can see that it only ever touches the graph at one time and never touches it two or more times. So it would pass the vertical line test. This would tell me that, yes, this is a function, okay? What about if it's not a line? What if it's a curve, right? Well, here's an equation. It says graph the relation represented by x equals y squared minus 2. Well, you might not have any idea what that looks like, but again, we can use the same strategy. We can make a table. So here's a table. Here I pick some y values because it's much easier to substitute y values in, square, and subtract 2 to find my x value than it would be to plug in x values. So here, in this case, I would, again, substitute my y values in and find the corresponding x values. So now I have my x and y coordinates. And then sketch the graph, right? So here are my points on the graph. I connect it with a smooth curve, and I can see here's my graph in blue there. And then I would take that graph and see if I can find the domain and range. So here the domain is that it would be, if you notice the domain is all the x values, well, it doesn't go off to negative infinity because the furthest left it goes is to negative 2, but it does go to positive infinity forever. So my domain would be that all x values, x would have to be greater than or equal to negative 2, right? All my x values have to be equal to negative 2 or greater. Now, my y values, right, going up and down would go to positive infinity because it keeps going up and up forever. It does go down to negative infinity, goes down and down forever. So my range would be all real numbers, right? Every real number would be part of the range. So determine if the relation is a function. Well, again, I'm examining the same equation, and I'm going to see if it's a function. The easiest way to do that is to do the vertical line test. If I do the vertical line test, I can see that it goes across. It will hit it 2 or more times in multiple places, right? So you can see it hits it in multiple places, right? All in this area going on forever. It's going to hit it 2 or more times. Another way that you can look at it is you can see that the x value -1 gets mapped to 2 different y coordinates, right? So the x coordinate -1 gets mapped to the same y coordinate, right? It happens here and here, right? That's one place where it fails the vertical line test. You can also see that it happens here and here, right? 2, -2, and 2 and +2, right? The same x coordinate gets mapped to 2 different y coordinates. That's another indication that it's not a function. All right, so when an equation represents a function, the variable, usually x, whose value makes up the domain, is called the independent variable. The other variable, usually y, is called the dependent variable because it depends, its value depends on x. So equations that represent functions that are written in functional notation, and our textbook calls it functional notation, but a lot of times you'll just see it as function notation. The equation y equals 2x plus 1 is usually written in function notation as f of x, right, equals 2x plus 1. So these two equations are the same equation. This is written in standard notation. This is written in function notation, okay? And typically, the f is the name of the function and the x is the input, right? And so your f of x actually replaces the y, right? And that's how it's read, f of x. And again, f is just the name, and then x is your input. All right. So if something is written as f of 4, it is read as f of 4, and the value 4 is found by substituting 4 in for each one of the x's in the equation. So therefore, f of 4 equals 2 times 4 plus 1, right? Anywhere there was an x, I'm putting a 4 in its place, right? So let's look at an example of this. If we're given function f of x equals x squared plus 2 and g of x equals 0.5x squared minus 5x plus 3.5, it says find each value. So here I'm given two different functions. I'm given the f function and the g function. And again, that leading letter is just the name of the function, and the variable on the inside is the input variable, right, where I'm going to be inputting values. So here it says find f of -3. So I know I'm using the f function, so I'm going to use this equation, right? And I'm going to be inputting -3. So instead of the x, I'm going to be inputting -3. So here's where I'm going to make my substitution in these x values. So I substitute my value in -3, and then I just evaluate it, right? I would do -3 squared, which is 9, right? And then 9 plus 2 is 11. So f of -3 equals 11. Right? So it's just as simple as substituting the correct value into the correct spot in the correct equation. Let's look at another one. This one says g of 2.8. So now I know that I'm using my g function, right? This equation right here, and I'm going to be substituting in 2.8. So here's my original function. My input is x, right? I'm going to be substituting in 2.8. And then I just have to evaluate it, right? Simplify it. So the first thing I would do is make sure I follow my order of operations, right? I'm going to square 2.8 first, then multiply, then subtract and add. So negative 2.8 squared times 0.5 is 3.92. 5 times 2.8 is 14. And then finish off my math there, right? Add that all together, and it gets me negative 6.58. So now I know that g of 2.8 equals negative 6.58. So given this one, we're going to do one last one. Well, this says f of 3z. Now this might throw people off. There's a variable inside, right? So again, we're still going to follow the same thing. We're going to use the f function, right? And anywhere there's an x, I'm now going to input 3z. So I substituted x out and substituted 3z in. So in this one, again, we're going to simplify. We're going to square 3z. So 3z times 3z is 9z squared, right? And then if you notice, that is as far as I can take it. I can't simplify that any farther because I don't know what z is. So the answer to this one is just that simplified expression. F of 3z equals 9z squared plus 2, right? So if your input has a variable, then obviously your output is also going to still have that variable because we don't know what that value is. All right, so that's it for us. Thank you guys for watching, and see you guys next time.